When you visit a favorite grocery store, either every day or every week, several brands compete for our purchase dollars. They want us to become their loyal buyers. An intuitive way of thinking about this process is to imagine a path taken by shoppers in your household. Think of your uncle or aunt sitting on your couch, seeing a TV ad that they like for a product. This might prompt you to buy that product later in the day from one of the stores in your neighborhood. We've all been there. Marketers use this fact to target you and I along the path to purchase using marketing strategies. This could involve a coupon, social media ad, or a weekly flyer that you get before you go to the store. And when you get into the store, you're prompted again to purchase the product through banner ads and demonstrations of delicious items. Why do brands do this? They do this to increase sales. This is referred to as marketing lift. Planning or optimizing a marketing campaign to maximize lift is a challenging problem. And this is the focus of shopper marketing optimization and inverse learning engine, or SMOILE for short. We provide an easy to implement and integrated framework that marketers can use to mine the influence of marketing strategies from several sources of data. And then they use this knowledge to plan future marketing campaigns.
Brands collect tremendous amount of data from multiple channels and they use it for future tactic planning. There are two major sources of data: primary data sets and secondary data sets. The primary data sources are usually raw data, and they range from point of sales data and historical marketing activities to seasonality information, while the secondary data sources are usually purchased from external vendors. For example, IRI and Nielsen provide information about aggregated lift. Having all this historical information, brands need to know the breakdown of lift due to individual shopper marketing activities. Think about a brand that wants to design a marketing campaign over 6 weeks at Walmart and Target. What the brand sees from the historical observations is the actual marketing activities and their corresponding lift values. At Walmart, demo is applied for the first 3 weeks, and the in-store discount is executed for the last 4 weeks. What the brand needs to know is the lift breakdown, which is the fraction of total lift attributable to demo and in-store discount. This is the lift attribution step. Having the attributed lifts, planning for future campaigns can be done by optimization techniques.
The birth of SMOILE came out of the realization that marketing attribution and future campaign planning are tightly integrated process and should be treated as such. Current statistical models used in practice don't necessarily capture this link, which leads to severe implementation burden. The way SMOILE overcomes this issue is to view both attribution and planning as mirror images of each other under the lens of sequential decision making. If you view future marketing campaign planning as a reinforcement learning problem, then marketing attribution is an inverse reinforcement learning problem that tries to mine the influence of tactics given a marketing campaign.
Modeling the tactic planning problem as a sequential decision-making process is important. Recalling the Walmart example, the demo in the first 3 weeks can affect the lift in the later weeks, since demo and in-store discount can interact with each other, and investing on one of them affect the budget for the other one. Since the marketers design marketing campaigns in a sequential manner, we make the mining and planning processes consistent via inverse reinforcement learning. Particularly, we enforce our model to learn a lift that assigns higher lift values to the existing historical marketing activities than any other possible plan. The resulting framework is SMOILE that joins data-driven optimization and inverse reinforcement learning can incorporate a large array of business rules related to planning, and it can be efficiently solved by commercial optimization solvers.